Hello, this is Rick from MathX, and today we'll be going over the number 10 from the AIME II of 2020. Now, when it comes to this problem, I have really mixed feelings, because this problem is not a bad problem, but there's an aspect in it I really don't like. When I took the test, I spent some time, and I almost got the right solution to the problem. But as I'm about to show you, in this problem, there's a really mean trick. So without further ado, let's just jump straight into the problem and get past this trolliness. Find the sum of all positive integers n such that when 1 cubed plus 2 cubed plus 3 cubed plus all the way to n cubed is divided by n plus 5, the remainder is 17. So this problem doesn't really give us much info. In fact, it only has one line, and that line itself is the question. It wants us to find the sum of all positive integers so that the sum of all the cubes up until n cubed, when divided by 5 more than that value, it provides a remainder of 17. So if we write this as a congruence, we get that the congruence we would get was 1 cube plus 2 cube plus 3 cube all the way to n cube will give us 17 mod n plus 5. So to simplify down this congruence, we can find the closed form of 1 cube plus 2 cube plus 3 cube all the way to n cube. Now, if you didn't know the formula, you could probably derive it on the test using values of n choose 3 and using the sum of squares, which you can also derive. But it's AIME, and you should be expected to memorize a simple formula like this. So if you memorized it, you would know that the formula for the sum of all the cubes till n cubed would be n times n plus 1 over 2 whole squared. So we'll get that this expression, n times n plus 1 over 2 whole squared, is congruent to 17 mod n plus 5. Now, it's going to be a little bit difficult to try to find out how this congruence will work in terms of mod n plus 5, because we don't really want to have an expression for what we're trying to find the mod of. Instead, it would be much easier to find out the mod of a single variable. So we can denote m as n plus 5. So using that, we can write this congruence as m minus 5, because remember, m is n plus 5, so normal n would just be m minus 5, times m minus 4, because remember, n is just m minus 5, so if we add 1 to that, that's m minus 4, over 2 whole squared is congruent to 17 mod n. So from here, we can just try to find out the numerical residue when this entire term is expanded. Because remember, if it has an m in it, it already is 0 mod m. So we just have to find out what the numeric value left over when we compute this expression is. So we can do this quite simply by expanding the top and then just paying attention to the final term. So when we expand the top, we get m squared minus 9m plus 20 over 2 whole squared. And we get that that's congruent to 17 mod m. So let's try to understand what will happen when we just take the numerical values in this. Right now, the only numeric values we have in this case are 20 and 2. So we only have to use these two values, because if we use any other values, their product will have m in it. Because if we take like 9m times 20 or 9m over 2, there's already m in that. And we already know that m is a multiple of m. M is 0 mod m. So we just need to ignore all the other terms with m's and just pay attention to the 20 over 2. So if we just look at this term itself, we get that 20 over 2 whole square is going to give us 17 mod m. Because if it has m in it, it's already 0 mod m. So just pay attention to the 20 over 2. 20 over 2 whole squared is congruent to 17 mod m. So if we expand the left-hand side, we get 400 over 4 is congruent to 17 mod m. Now, when it comes to using congruences, we can't divide congruences. It's just a rule that's in place when using congruences. And there are many counterexamples to prove it, but it's just a rule we can't do. So instead of dividing this to get 100, we're going to actually have to multiply this by 4 in order to get 400 is congruent to 68 mod m. So then, if we subtract 68 from both sides, we get 332 is congruent to 0 mod m. Now all that's left to do is find all the values of m that satisfy this congruence, check if those same values of m satisfy the original congruence, and then convert those all to n's, because remember, we're supposed to be finding for m, which we've expressed as m minus 5. So let's get to the first part, trying to figure out how many values of m that satisfy this congruence will also satisfy the original expression. So I'm going to make some space over here to do that. So if we know that 332 is congruent to 0 mod m, that must mean that m is a factor of 332. The good thing for us is 332 has a very distinct prime factorization and doesn't have that many factors, with this prime factorization being 2 squared times 83. Now, we know that m itself has to be greater than 17, because otherwise it can't leave 17 as a remainder. So we have to take all of the factors of 332 that are greater than 17 and include those in our list. Because if it's less than 17, like 2 or 4, it can't give us a remainder of 17. So all the factors of 332 greater than 17 are 83, 2 times 83, which is 166, and 332 itself. Now, this is where the troll part of the prompt comes in, because even though these values satisfy the congruence over here, not all of these values satisfy the original expression. It turns out that the AIME II problem developers wanted you to actually test out each of these values to confirm that they worked in this original congruence. And if you just test them out by using a lot of computation, you'll find that 83 and 166 do work, but 332 doesn't. So, just like that, even if you got all up until here right, you're going to mess up the final steps because you just missed out on that slight computation. And this teaches us a very valuable lesson. You always have to recheck your problems on AIME problems. Because even if you did all the math right, you never know what twist they'll throw at you at the very end. So then, because once we do the calculations, we see that 332 does not work, we cancel that off our list, and we know that the only possible values for m are 83 and 166. So since m is n plus 5, we have to subtract both of these values from 5 to get our values of n. So that means one of our values of n would be 78, because 83 minus 5 is 78. And another would be 161, because 166 minus 5 is 161. So then we take 78 plus 161. Doing so, we get 239, which is our end answer to this problem. So if there's one thing you need to take away when doing this problem, when it comes to the math wasn't even that hard. In fact, the math is actually below where it's supposed to be, considering that this is an AIME number 10. But you just have to be able to recheck your work, because you could be another unfortunate person who does all this math right, but then messes up on the final step because they didn't check their work. So remember, always check your work on AIME problems.